Molecules that have more than two atoms, or polyatomic MO molecules, have more complicated symmetries and more complicated molecular orbitals. So let's look at a fairly common example that you would have done in freshman chemistry. Let's look at the carbonate anion. So when we draw let's first look at just what we know about this from general chemistry. When we draw a Lewis structure of the carbonate anion, we have carbon in the center, and we have oxygens connected to the carbon, and we have one double bond, and two of the oxygens are connected by single bonds. When we think about this molecule in terms of a local bond model, or a valence bond model, we think of the carbon as being sp2 hybridized, and we think of it as using its sp2 hybrid orbitals to form bonds to each of the oxygen atoms. And then there's a leftover p orbital on the carbon, and there's a p orbital on this oxygen, and those can overlap to form the pi bond. And so we think of this as having sigma bonds. So there's a sigma bond between the carbon and each of the oxygens, and then there's a pi bond that is formed between the carbon and the oxygen. And that's the normal way that you think about thinking about the bonding in carbonate. It gets a little bit more complicated because we know that there is resonance in this molecule, so we can draw this double bond in any one of three positions. And because we can draw resonance structures, we know that in fact this double bond is shared and is actually smeared out or delocalized over the entire molecule. So we've gone from, when we include resonance, we've gone from a local bond model where the bonds are completely localized between two atoms to a delocalized bond model where at least one of those bonds is delocalized over the entire molecule. Remember that in the molecular orbital picture, we are actually solving for the energy levels for all electrons together to form a given state, a given energy state of the molecule. And the wave picture of the electrons for that particular energy state are going to be the superposition of all the electrons in the molecule. Again, that's not a very enlightening model to use because we can't really tell where the electrons came from, and it doesn't help us think about the bonding in that molecule. And so we use a sort of hybrid local bond model where we make these symmetry molecular orbitals that conform to the symmetry group that the molecule belongs to, and that allow us to think about which atomic orbitals, but again, we're going to use atomic orbitals from all the atoms in the molecule, which of those atomic orbitals have the right symmetry to mix to form a particular molecular orbital that will have that same symmetry. And so in the molecular orbital picture, there are no localized bonds. They're all delocalized. They all come from electrons from all the atoms in the molecule. And so when we think about resonance, going from a completely localized model where we can say exactly where those electrons are to a partially delocalized, so we've at least delocalized the pi bonded electrons. When we go to the molecular orbital picture, we are going to a completely delocalized model for the bonding. When we form these molecular orbitals, we have to end up with the same number of molecular orbitals as the number of atomic orbitals that we started with. And so even if we just consider the filled orbitals on the carbons and oxygens, there are 5 filled orbitals, 1s, 2s, and 3 2p orbitals on each of the atoms So there are four atoms times 5 orbitals on each atom gives me a total of 20 molecular orbitals, even if I just consider the filled orbitals. And in reality, I need to consider even those that are not filled if I want to be able to model the excited states of this molecule. So at the very least, to describe bonding in the lowest energy state, I need at least 20 molecular orbitals. So let's take a look at just a few of those molecular orbitals. I've shown a completely bonding molecular orbital that's completely symmetric here. There's this molecular orbital that seems to have a nodal plane in the plane of the molecule. And then we have this molecular orbital that has a nodal plane right at the oxygen here and here, and a nodal plane between above and below the plane of the molecule over the carbon and the oxygen. And then we have this one, which has a nodal plane right in the middle of this carbon-oxygen bond, and then a nodal plane that is at each of these oxygens. And then we have this one, which has a whole bunch of nodes. And in fact, there's a major node right at the carbon atom in this molecular orbital. Notice that this is only just 5 of the possible 20 bonding molecular or 20 molecular orbitals that are formed from the filled orbitals of the carbon, oxygen, and nitrogen atoms. You also need to remember that this molecular orbital picture is not unique. There are other ways that I could form molecular orbitals, and they wouldn't necessarily look exactly like this. So we've picked a particular way of showing these molecular orbitals, and again, they're going to be ones that conform to particular symmetries based on the symmetry group that CO3 2- belongs to. So what symmetry does for us, it doesn't help us decide what these molecular orbitals look like, but once we know what they look like, it allows us to characterize them in terms of a representation in the point group for the molecule. So let's, for instance, just take this this molecular orbital right here and think about how it transforms in the D3H point group, which is the point group for carbonate. D3H has, in addition to the identity operator, a C3 operator. It has 3 different C2 operators. It has the sigma H, and it has 3 different sigma V operators. And it also has an S3 operator. So I can think about this particular molecular orbital and think about how it transforms in under each of these different operations. Now, what's going to be important is that I establish a coordinate system for my molecule, and the coordinate system that I pick is going to influence the reducible representation that I obtain for a given orbital. So you could pick any coordinate system you want, but typically it's best to put the highest symmetry axis as the z-axis. So our C3 axis is that axis right there. And this puts the molecule in the xy plane. So now what I'm going to do is I'm going to imagine operating with each one of these DH3 operators on this particular molecular orbital and see what happens. And so if I rotate about C3, so I rotate about the z-axis 1/3 of the way, then I will end up exactly where I started. So it'll look exactly the same if I do that C3 rotation. If I rotate C2, so any one of these bond axes, I'm just going to flip it over and it's going to look exactly the same. Same thing if I reflect in the sigma H plane, which is this xy plane. And if I rotate or reflect across any one of these sigma sub v planes, that's the plane that is parallel to the z-axis but includes one of these bonds, then I'm just going to reflect it back over to itself, and it's going to look exactly the same. And if I do the improper rotation, where I rotate through a third and then reflect over the horizontal plane, it's also going to look the same. And so this particular orbital is completely symmetric. It has a representation that has all ones, and the representation in the D3H point group for that is A1 prime. If I do the same thing using this orbital, I will find that I get the characters that correspond to A2 double prime representation. You can assign the term symbol or representation for any given molecular orbital using table 6.5 in your book fairly quickly. So if it's singly degenerate, it'll either be an A or a B representation. And the difference between A and B is whether it's symmetric or antisymmetric with respect to the principal rotation axis. And then depending on what the degeneracy is for the representation, so if I had two of these that look exactly alike, they're just oriented in different directions, then it would be an E. And then you look at the symmetry with respect to the inversion operator if it is part of that group, and that will tell you whether it's G or U, just like for diatomics. The prime and double prime designation comes from whether the molecular orbital is symmetric or antisymmetric with respect to that horizontal plane of reflection. And so if you have a sigma sub h in your particular point group, then you are likely to have primes and double primes on your terms.